Great.
Okay, I'd like to welcome you all here to our Air Source Heat Pumps 101 webinar here on April 25th, 2023. Very happy and thankful to be joined by our consultants over at Abode. That would be Ryan Keith, and our featured speaker today will be Terry Bean. At this time, I'm going to hand it over to Ryan, and he's going to get us going. So Ryan, take it away.
Great. Thanks, Kevin. I'm glad to be here. I'm with Abode Energy Management, like Kevin said, with my colleague here, Terry Bean, who will be presenting to you folks tonight. Just a quick itinerary for the presentation here, and then I'll hand it off to Terry to dive into the content. We'll be starting with just a little bit of background on the company Abode Energy Management, what we do in Massachusetts and beyond, and a little bit of background on Terry's experience in the industry as well, and sort of his involvement in our programs with Middleborough Gas and Electric Department. We will cover the Middleborough Gas and Electric Department rebates. I think we might have moved that to the end of the presentation, but we will be touching on that. We'll provide some summary information on heat pumps, an intro to the technology, and then considerations for how to best utilize heat pumps for electrifying homes and decarbonizing. And then from there, we will, like I mentioned, touch on those Middleborough Gas and Electric Department rebates that are available to Middleborough and Lakeville residents. And we'll recap on the different services that are available through the programs before we open it up for a question and answer session. And I will pass it over to you now, Terry. Thanks.
Thank you, Ryan. Thank you, everyone else, for being here. As Ryan mentioned, I work for Abode. Initially worked in the field on the weatherization side of our program, dealing with contractors who help insulate and air seal people's homes. And we'll talk about that a little bit in terms of what that might mean relative to heat pumps. And in the past 6 months or so, I have transitioned to working on the heat pump side of our business. I spend my days speaking with homeowners from a variety of municipal light plant cities and towns, offering consultation services and other services to help them understand heat pumps and what's the best way to think about selecting their equipment, designing the systems, how to talk to their contractors, etc. So hopefully we'll get into some of that here today and add some information for you so that you're better educated when you do talk to contractors about heat pumps. Okay, so in regards to Abode Energy Management, we are a lead vendor on the Mass Save program. And we work with contractors who do a lot of the weatherization, as I mentioned, and that's where I was working earlier as part of my career here at Abode. We're also a program administrator for these municipal heat pump programs, and we have also some statewide air source heat pump programs that we are administering. We have experience internally with our staff as contractors, in home performance contractors, with folks who do air source heat pump sales and installations. We've got some expertise with residential solar PV installs and some other experience as well. So we're pretty broad here at Abode. We've amongst all of our staff, but an array of knowledge in regards to decarbonization and electrification. We are largely certified with BPI, which is the Building Performance Institute. And we also have some other certifications in-house, depending on the individuals. So we can provide high quality building science-based information. And that's how we gear our programs and our interactions with both homeowners and with our municipal and statewide clients. And we do offer some technical consultations as well for residential home energy efficiency and some decarbonization program design. So we go to the next slide. And here I am. So some of my background, as I mentioned, started as an inspector years ago for a different company on the Mass Save program and transitioned to Abode a few years ago, which was a good good move for me and a good move for us as a company to get back involved in the Mass Save program. So I've done inspections on both residential and some commercial installations of energy efficiency measures and equipment. And since August of this year, I have been focusing on the heat pump area, and in specific, conducting consultations, as I mentioned, for mainly MLP customers, although we do serve some market rate cities and towns as well. And when I'm not working, I like to get out and do some kayaking, some surfing when I can, and hopefully be able to do some this summer when the water gets a little warmer and the weather gets a little warmer. So looking forward to that. Okay, so we're going to talk about heat pumps today. And best place to start off with is, what is a heat pump? Okay, so the name kind of gives it away, really. It's an item that is not really a piece of equipment that is not really actually creating heating. It's moving heating from one place to another. So in the summertime, it's going to be moving heating from inside of your home, heat energy from inside of your home to the outside. That's what's going to cool your home. And in the wintertime, it's going to move heat energy from outdoors to indoors. And in the summertime, that's not, dissimilar from central air conditioning systems that folks may be aware of, have some experience with, or frankly, even a refrigerator, where it's moving that heat energy from inside of the box of that refrigerator to the outside. The presence of cold is not really the addition of cold, it's the reduction of heat energy. So heat pumps are reducing that heat energy, similar to central AC, from inside of your home in the summertime. But they also have the ability to reverse that and deliver heating from outdoors to indoors as well. Go to the next slide. And again, just like a water pump doesn't actually create water, it just moves water from one place to another. A heat pump, and again, why we call it a pump, it's because it's moving heat energy from one location to another. So the heat energy has not been created by the pump itself. It's been created by other forces, and we're going to take a look at that in a little bit. And here we are. Where does that heat come from? Okay, so we're going to be able to get heat in the wintertime from the atmosphere. Okay, and as you can see in this diagram here, that's going to be the sun. And it doesn't seem very warm outside to us as humans in the wintertime. It's cold. However, we don't live in outer space. It's not absolute zero outside. So there is some heat energy available in that air. If we can effectively capture it, heat pumps can, and then they can deliver it inside of your home. And you can see in this graphic, what it's estimating there, what it's representing, is that the majority of the energy that's going into that heat delivery is coming from the sun itself. So it's not as if the electricity that goes into the system is being used really for heat generation. It's more for heat delivery. Okay. Go to the next slide. And then consequently, in the summertime, it's a similar proposition where, again, that electricity that goes into the heat pump system is being used to move that heat energy from inside of your house. And we all know that houses can get warm with the sun radiating on them in the summertime. So that heat is amply available inside a home, and we can move it to the outside and cool a home using the same technology. Okay, so how does a heat pump work in terms of the components? And really how it works, it's pretty elegant. It's fairly simple, although it may seem a little bit magical. There is refrigerant in the system, and the refrigerant is used to capture heat and deliver it. This is what the mechanism is by which the heat is pumped from one location to another. But what's required to do that is a pressurization and depressurization of that gas. So when it gets pressurized, the heat molecules that are in that refrigerant that has been converted into a gas, because it's so sensitive to heat gain that it will actually boil in very cold temperatures. And when it gets compressed, when it gets squeezed, put under pressure, that's when we can extract heat off of it. So we can send pressurized gas to indoor units to extract heat off of them in the wintertime. And then we could send that same pressurized gas to the outdoor unit to send that heating to the atmosphere in the summertime. So it's this combination of indoor units, outdoor units, refrigerant traveling between the two, and pressurization and depressurization of that refrigerant that kind of makes the magic of a heat pump. Okay, so you can see the arrows are telling us what direction the refrigerant is moving. So in this case, this is in the cooling mode, right? So the pressurization is happening, heating up that refrigerant and sending it to the outdoor unit, in this case, as represented by that yellow arrow, where that heat energy can be extracted from that hot gas in evaporated off into the air. So that's how we're cooling a home. So when we're cooling a home, it's just the same operation as when we're heating a home. It's just in reverse, okay? So you can see, again, this is another graphic sort of representing that. The roles of the indoor units and the outdoor units will change depending on the season. So folks who have a central AC system are familiar with calling an outdoor unit a condenser. Well, that role actually will change back and forth with a heat pump system depending on the season. So it can be a condenser in the summertime and a evaporator in the wintertime. So what can happen here is because these roles are changing back and forth, you don't really need to use the same nomenclature to describe these units. You can simply call them an indoor unit and an outdoor unit because the roles change, and that's perfectly fine, and that makes it kind of simple to think about. We can go to the next slide. Brian is highlighting the compressor and the evaporator there. Actually, the compressor and the expansion valve there. So in this slide, we are looking at something that something else that is unique about a heat pump in terms of its operation, and that's the ability to do what we call modulate. And now modulation is sort of unique to heat pumps. If you look at that wave pattern of the blue line up and down, that is something that looks a lot like what your existing combustion equipment, your oil system or your gas system, might operate like. So if the temperature that you're attempting to maintain is a straight line across that graph, the operation of your combustion heating system, it's kind of a, fully on and then off proposition. And so you can sort of see that represented in the peaks and the valleys of that sort of wave pattern across that. There's quite a bit of variability for it to average out to that temperature. But heat pumps have much more control of their operation. They have a lot more variability in terms of how quickly they can respond to heating temperatures and how controlled they can be when they're doing it. So with that inverter that allows the heat pump to do that, you can see that yellow line representing the heat pump that has modulating capacity. It's much closer to the straight line. The peaks and valleys of that wave pattern are not nearly as exaggerated, which means that that translates to more consistent conditioning of the air and more comfort. And it can also represent more efficiency in terms of its ability to maintain temperature over time and not have to operate at a high capacity and then essentially shut off. So we really want that yellow line, that modulated functioning of the heat pump that gives us the best operation, the best comfort, the best efficiency out of the system. So we can go to the next slide here. Okay. All right. So this is where we're talking about the capacity of a system. And Capacity is something that you're going to hear about when you start talking to contractors about your home's heating and cooling requirement. Okay, it's going to be described in terms of the overall capacity. That's kind of an overall size of the equipment. However, there's also the capacities, since we're talking about air source heat pumps, and since particularly in the winter time when we're heating, which is when we're doing most of our conditioning of homes in New England, there's less heat energy available, obviously, as the temperature gets colder outside. So heat pumps do not all have the same capacity at lower and lower temperatures. So there are heat pumps on the market today that are much more like the heat pumps that were available 10, 12, 15 years ago that didn't really much have a very good capacity in very low temperatures. So sometimes you'll still hear folks say, well, I've heard a heat pump is not effective in cold temperatures. That really depends on the model that you're looking at and its capacity at the very low temperatures. And so what can help with modulation is delivery of that capacity at very low temperatures in a more consistent fashion, and the ability of that system to essentially capture sort of small bites of heat energy from outdoors and redeploy them indoors in a consistent fashion, keeping the temperature much more even and not having to work as hard to meet that initial temperature. It's going to maintain temperature, and that's going to help it also maintain its ability to provide heating in very cold temperatures. Okay, so now we're taking a look at the ways, so we talked about earlier, outdoor units and indoor units. Now, the outdoor units are going to be fairly consistent. There's going to be some difference in size, obviously, of the outdoor unit and a little bit in terms of its form factor. Mostly they're sort of these vertical units, but sometimes they're more square. However, the indoor units do have some variation. So we've got two general categories of indoor units. You've got ductless units, which is what we're seeing here. Also, we can just refer to them as non-ducted is another way. So in this instance, refrigerant lines are essentially running directly into these indoor units, right? So folks may be familiar with the unit on the upper left, which is a wall-mounted mini split type system. A lot of folks have seen many of these. They're frequently installed. You can even see them installed commercially in restaurants and such. Really, the refrigerant lines are sort of running right through the exterior wall into this unit. You have other options for indoor delivery. A floor mount next to it in the center is another option. Floor mounts have the refrigerant lines coming up from underneath. They offer some flexibility. They could even potentially be located on an interior wall if there's space in a basement to run the refrigerant line. So that gives that additional option. Some folks like the form factor. If someone's replacing, for instance, a steam system and they want to remove radiators, that can slot right into a spot where a radiator was. And there may be some advantage to having heating in the lower part of a cavity. If you've got high ceilings, for instance, that might make for a more comfortable lower third of the air column in that area. And then you also have on the right-hand side these ceiling cassettes. These are, very nice looking in some regards. They sit flush with the ceiling cavity. However, they do have some additional technical requirements. They can only serve up to an 8-foot ceiling height. They have to be within several feet of an exterior wall. In some instances, they'll need to be serviced from above. So in many cases, they're better suited for second floor applications where there's an attic above. But they do tend to cost a bit more to have installed because obviously there's more labor. But for folks who really are interested in that sort of thing, I know a lot of architects I've spoken with are very interested in that sort of form factor. That is also available. Now, one thing about those units before we move on, just one second, is that they do have some variation in how small they can get in terms of their capacity. So that's one thing to consider with these units. The smallest capacity units right now that are available are those wall-mounted units. So if you're limited in terms of your total overall capacity, that might influence your choice of a non-ducted solution. So we can move on to the ducted solutions now. Okay, so now we have ducted solutions. And these again come in a variety of options. So we have small ducted solutions that are designed to treat a couple of rooms or potentially several rooms, depending upon what kind of air pressure they can accommodate in that ductwork. So you do have scenarios where you might be able to fit a small ducted unit into a fairly small space, maybe a small attic, or even potentially the attics that you see at the eaves of homes that we refer sometimes to as knee wall attic spaces. Those might be something that could fit into those types of units. Also, for ducted systems, you might consider them in basements coming up through flooring. So there's a few options in terms of where you're going to put a ducted system. You also have whole home systems, and these could be, existing centrally ducted systems. Perhaps somebody already had central cooling on ductwork, which is a good candidate for maybe a heat pump replacement. One cautionary note about existing ductwork: if it's only been used for heating, or if there's some other constraint on the ductwork, there's no guarantee that it will function properly with a heat pump. So that's one of the questions that needs to be asked of a contractor if ductwork is present, whether or not that ductwork is suitable for a heat pump application. Also, just in general, the limitations of the design of the ductwork aren't going to be solved by a heat pump. So if you have central returns and supplies, say in rooms with closed doors, that's going to impede airflow, and a heat pump's not going to change that. However, if you get a heat pump that is modulating, it should be a lot more even than, say, the rush of warm air that you might get from a gas or oil furnace with a central system. Okay, so here's some of the variations in terms of combinations of outdoor units to indoor units that you could potentially consider as part of a design. So on the left, you see that single zone, which is what oftentimes referred to as a single zone mini split. And we also refer to this as a one-to-one system. This is where you've got one outdoor unit that is sending its conditioned refrigerant to one indoor unit, in this case, a wall mount unit. And these are great units. They have a lot of flexibility in their ability to drop into that modulating mode and operate very efficiently. Because you're seeing refrigerant lines running directly from the outdoor unit to the indoor unit, there really isn't any loss in efficiency going through air handlers or ductwork or things of that nature. So depending on the space, these are great units. For example, I spoke with a customer a couple of months ago who had a third floor conditioned area where it was wide open and she needed to add one system up there. And this is exactly the type of system that she added, and it worked out perfectly. Now, the middle example is a multi-zone system. So in this case, what they're displaying is something we call mixed use, which is where the outdoor unit is sending its refrigerant, in this case, to both a non-ducted unit, which is the wall-mounted split system, but also, in this case, to a couple of air handlers as well. So multi-zone systems can serve all non-ducted solutions. They can serve ducted solutions. They can serve a mix. So oftentimes we find that a mix is a nice solution where you could put non-ducted equipment in larger areas that are open and communicating, and consider maybe ducted air handlers for smaller divided areas. And then you've got, in the third example on the right, you've got a multi-zone system with these branch boxes. So you can conceivably have one outdoor unit with a large enough capacity to handle the entire heating and cooling load of a home. And then using branch boxes, you can split those refrigerant supply off to multiple units off of that branch box to serve several areas. In general, it's still a good idea if you're looking at multiple indoor units to consider breaking that overall system up onto more than one outdoor unit. Granted, there's some additional costs with adding an additional outdoor unit, but it gives you some redundancy of operation. It gives you a bit more flexibility in the system, allowing it to modulate, keeps the total number of zones on a given system a little bit more limited. So that's something that you might consider, but these types of systems are available. Okay, so when we're looking at your home, we're thinking about how to design a heat pump. This is where we can run into some challenges, especially depending on the distribution method that we're thinking about. So in this case, with this home, they've got one unit hanging on a wall that they're intending to serve multiple areas, some with closed doors and obviously a lot of walls. There is a living space with the cathedral ceiling, so there's a lot of air volume there. So you could get quite a bit of variability in that space because there's multiple different types of areas that are being impacted by either solar gain or their position, relative to south facing, et cetera. So sometimes these non-ducted systems can work well in areas that are subdivided, but if they're modulating and they're running consistently, there is ample time for the air to work from room to room. However, there is some limitation, and they can't really deliver their heating. That fan that's in that unit that's recirculating the air from the interior of the home does have its limitations in terms of how far of a distance it can send that air. So you might be able to get it in this particular scenario, fairly far down the hallway, but perhaps it doesn't make its way well into rooms. And you might see quite a temperature variance from one space to another. So maybe that's not the most advantageous design. However, we do still want to be careful when we're thinking about non-ducted units in terms of how we consider them with multiple divided spaces. So we can go to the next slide. Okay, so this is where someone has decided to install multiple non-ducted units in several spaces. So sometimes this can be okay if the areas are larger and they're communicating from space to space, and that non-ducted system is sized appropriately. But as I mentioned earlier, there are some limitations in terms of how small these systems can get. So even the smallest system could potentially be oversized for a given area. If you've got too many of them, and sometimes we do see this where folks believe that, if they've got several bedrooms, for instance, that they might need one split system in each of the bedrooms. That could be a scenario where you're oversized for those individual areas. You may just have too much overall capacity, and there's no advantage to having too much capacity for a heat pump. In that case, you may cause the system to not be able to modulate, and that will greatly reduce its efficiency because it's going to use more electricity. It's going to always be working in its maximum operating capacity, or whenever it is working, and it might basically turn off after it reaches temperature. If it does that when it's cooling, it might not run long enough to properly dehumidify the house, and that could cause a moist atmosphere that's uncomfortable. It could maybe even cause a moisture issue in the home if it's severe enough. So there's no advantage to oversizing systems, and that's where you can get into a little bit of a challenge with the non-ducted equipment in subdivided areas. So we can move to the next slide on this one, because I think this will speak to this a bit. So here's an example of combining non-ducted and ducted equipment. So we saw that a couple slides back where we saw those mixed use outdoor units. In this case, you've got non-ducted equipment that is serving the larger area with more volume in communication from room to room. And you've got a small ducted system that is serving the smaller subdivided areas. So you don't have to worry about oversized equipment in the smaller areas like bedrooms, because there really isn't any individual units there. You've got an air handler that is ducted to those units. And you also keep the total number of zones on the system more limited, which means it is a more flexible system, more likely to go into that modulating mode and run in the most efficient manner. So that's going to help you keep your operating costs lower, and also it's going to keep your temperature more consistent throughout the year if you can size it right. So that's what we want to do with heat pumps. Okay, and we're going to talk a little bit briefly about heat pump water heaters. So we went through the mechanism by which heat pumps are capturing heat energy from outdoors, in the case of an air source heat pump for your home, and delivering it indoors in the wintertime when it's heating your home. Well, imagine that same essential functionality sitting basically on top of a water tank. And instead of pulling its heat energy from the outdoor air, it's actually capturing it from your basement. And obviously, there's more heat energy in your basement than there is outdoors in the dead of winter. But in the summertime, additionally, when it's pulling that heating out of your basement, it's going to cool it down a little bit and dehumidify it a little bit, right? Because it's now acting the same as a air source heat pump when it's cooling your home in the summertime. So we can extract that heat energy from your basement and use that to heat hot water. Now, what differentiates this from your standard electric water tank is the same way that air source heat pumps are differentiated from electric resistance heating, in that the electricity that's going into this is for that same movement of refrigerant and compression and expansion of the refrigerant to capture and release heat energy. So again, that's where you get the efficiency. Electricity is going in for moving that heat from one location to another, in this case, from your interior atmosphere into the water, versus making that heated water. So it's more efficient than a standard electric tank, and it's more efficient than a combustion appliance tank as well. So something that you could look into as well. Okay, so we can talk a little bit about the benefits of moving to electrification overall. So, obviously carbon fuels are used in many cases to create electricity. In some cases, they're used more directly. So if folks are, burning oil to create heat in their home, or burning gas to create heat in their home, they're using it directly. In the case of electric resistance, carbon fuels could be burned. It could be coal, it could be gas, it could be diesel. It is being burned to generate that electricity. So when you compare various types of heating and their impact on carbon in the atmosphere, you can see where heat pumps near the top of the graph here are using or creating less tons of carbon over a 20-year period than other heating sources. Now, part of that is because they're not using that electricity, for the creation of heat, as we've mentioned. The heat's being manufactured by the sun for us, so we gain all that efficiency. So we're using less electricity in any case, regardless of what the source is for supplying that electricity. And it also gives us variability in terms of what that source is. So we can add renewables to the mix and other, in the future, additional non-carbon, means of creating electricity. So there's a lot of flexibility in a heat pump in terms of where the electricity comes from, and therefore its impact on carbon into the atmosphere. Okay, so when we're looking at, say, electrification overall for the whole home picture, heat pumps are really an extremely important part of that, because we're really using most of our energy in a home to heat our homes in New England, right? If we're living in Arizona, we might be using it to cool our homes, but we live here in Massachusetts, so we're using our energy to heat our homes. And that COP term that you see there on the left, that is referred to something called the coefficient of performance. And that's just really a fancy way of saying how much electricity or whatever energy type is being used by the system, how much is going into that system versus what we're getting out of the system. Okay, so you can see that energy input as the denominator there. So we are looking at these various types of heat sources, and you can see that when you're looking at a combustion type of heat source, the maximum you can get is going to be well less than 1 of a COP, and 1 basically is analogous to 100% efficiency. So folks who have oil systems are maybe familiar with their 80 to 85% efficiency of an oil system if it's running well. Natural gas systems, depending on the type of system, might be an 87% efficient system, might be a 96% efficient system. So regardless, you're never going to get 1 because there is no fuel that burns at 100% efficiency. If you're using electric resistance at your home, you're getting 100% efficiency because there's no combustion there. Somewhere back at power plant, there's still fuel being burned, so you're never going to get above 1, which is 100% efficient. But again, that's partly because the fuel that goes into those systems is all being used for heat generation, not heat transference, which is what a heat pump is doing. It's right, again, going back to that water pump analogy, it's not making heat, it's just moving it. The heat's already been made, so we're capturing the resource and just redistributing it. And that's what the electricity is being used for. So that's why you can get that proportional increase in efficiency out of a heat pump that it can't be compared with any of the other heating options that are available. So it's a key element if you're thinking about electrification in your home. Okay, so if you're looking at overall electrification, one of the things that you might consider, certainly, you can't go wrong with weatherization in your home. So increasing your insulation, increasing your air sealing, your home's going to lose heat a couple of different ways. One of which is going to be the movement of heat out through materials. That's conduction. That's what the R value is in insulation, is resistance to conduction. So when you are increasing your insulation levels, you're slowing down the rate that heat wants to move out through your walls, through your attic spaces, move to the outside, okay? And when you're air sealing, what you are slowing down is the convective loss of heat. So that's when you heat up air in your house, it rises like a hot air balloon, it hits the ceiling of your top floor, and the pressure wants to force it up and through any cracks and crevices into your attic space and out through your home. So those are the 2 ways. We also radiate some heat out of a home as well. But in general, what you can do is weatherize your home, no matter what you're using for a heat source, is going to reduce your home's overall heating load and consequently also your cooling load, because insulation works both ways, right? It helps to slow down the exfiltration of heat in the wintertime and the infiltration of heat in the summertime. So by all means, consider weatherization as your first place to start, regardless of what you're doing in terms of a journey to make your home more efficient. And then another thing you're going to want to consider, and if you're looking at heat pumps right now, you're going to want to ask contractors about this. What is the existing amperage of the main electric panel in your house? You're likely going to need at least a 200 amp service. Some folks are considering larger services up to 400 amps if they are planning on adding significant additional electrification to their home, like multiple electric vehicles, if they're considering adding batteries in solar PV, etc. So if you're thinking about upgrading your panel, make a wish list, like electric stoves, for instance. If you're going to convert from any kind of a gas stove, electric water heaters, when you're thinking about upgrading your panel, make your wish list of all the things that you want to do in the future so that you get that taken care of at that time and you are prepared for anything that you will add on or are even considering adding on in the future. And so, of course, if you're adding things like solar PV and you have that with, a heat pump solution, there are times when the electricity that is running that heat pump is going to be generated by those solar panels. So that's just obviously more increased efficiency. And likewise, you might be able to charge your cars and such. So you can see that there are ways potentially of really markedly reducing your overall fuel usage, your overall carbon impact, and in some cases, sort of your independence of operation as well. If you have a solar array with some storage, that may be something that you can depend on to last through maybe a weather event for a period of days and be more independent in that regard. Okay, so here's the MGED heat pump electrification rebates. I think Kevin might be willing to speak about this at this point.
Sure, thanks, Terry. And I'll be very brief, but I would refer anyone back to our website where we did a full hour-long webinar last month that addressed the specifics of all our rebates, how to get them, and what that entails. But quickly, an MGED rebate offers apply to residential electric customers only who reside in or own a single family detached, multifamily attached, up to 4 dwelling units, or mobile home or apartment condo up to 4 dwelling units in Middleborough or Lakeville. All homes will receive an Abode full free home energy evaluation audit. All qualifying equipment must be listed in the CEE AHRI verified directories as meeting or exceeding the efficiency minimums and be chosen from the Northeast Energy Efficiency Partnerships NEEP's current cold climate air source heat pump specification list. There are just numerous configurations for all qualifying equipment. So, when you get down to the brass tacks there, lean on your contractor installer to, find specifics for that. But for our rebate program, for a hybrid heat pump water heater, obviously Energy Star, rating required, up to $500 rebate amount, no more than half the install cost, and only a single unit per residential home. For our air source heat pump, mini splits, multi-zone, and single based, after completion of the home energy evaluation prior to installation, rebate will be no more than half the installed cost, up to $500 per ton. Minimum Energy Star ratings required. For the mini split, that rating, a SEER rating should be, in SEER is the seasonal energy efficiency ratio, should be 18 or greater, and the HSPF, or the heating seasonal performance factor, should be 10 or greater. And for the central multi-split ducted mini split, it's a SEER is 16 or greater, and HSPF 9.5 or greater. And also, if you were to replace the central air conditioner or an older heat pump or the whole house, again, after the completion of the home energy evaluation, the rebate will be $500 per ton, up to $2,000, and not to exceed more than half the total install cost. And also, you would receive a $500 bonus earned when replacing the entire central AC unit. Yeah, that's all I have for that one. And also could refer to, and I'm reading along here, this federal tax credit from the IRA, which was rolled out late last year and still seeing some modifications this year. The tax credits are 30%, and that was 30% of equipment and up to $2,000 for the year for installation cost. Next slide.
Great. Well, I think that brings us to our Q&A here, so I'm happy to open it up for questions. If people would like to send any in the chat, that is an option, or if you use the raise hand feature, which I believe you have, we can also allow you to unmute yourselves to ask questions out loud. Just taking a look back through the chat here. So yes, the webinar is recorded. We will be making that available on the Middleborough Gas and Electric Department website. And Kyle will be planning to send out the link to everyone who's registered here. All right, so we're hearing from Maureen. How does air source heat pump compare to ground source heat pump for efficiency?
So I'll take that one. So in general, ground source heat pumps can be more efficient systems. Ground source systems are drawing, what is essentially 50 degrees Fahrenheit, several feet below the ground, anywhere in the world, any time of the year. That said, efficiency is not your only consideration. You also have your install cost and whether or not that relative efficiency is worth the additional expense of a ground source system. However, there are ground source system specific contractors in Massachusetts. And if you were going to look into that type of equipment, I would highly suggest that you speak with contractors who have specific experience with those types of systems.
Thanks, Terry. And looks like we got one here from Kyle. Are heat pumps now practical as the sole source of heat in our single digit temps? I'll let you handle that one and then can jump to the next part of the question.
Sure. Yes, in short, but also sort of with an asterisk, that depends. If you select heat pumps that are more like the original style heat pumps that don't maintain their capacity to effectively gather heat energy in very low temperatures and redeliver that, then no. Even if the equipment is sized appropriately for your home's heating and cooling requirement, in very low temperatures, that type of equipment would struggle to maintain its rate of heat delivery in order to keep up with the rate of heat loss out of your home. So if you're looking for a whole home replacement, you need to make sure that you're talking to your contractors and let them know that that's the kind of system that you want and that you get quoted on equipment that does have a high level of maintenance of its capacity in very low temperatures. Ideally, we like to see 100% maintenance of its capacity at 5 degrees in order for it to be considered something that's suitable for a whole home replacement.
And then I'll jump back to the question that was just asked, but Maureen is asking a related question about how do heat pumps perform in super low temperatures, such as maybe the negative degrees.
So there are heat pumps that have ratings down into negative temperatures. In some cases, -15, -17, they're actually rated for their delivery. They do tend to lose a little bit of their capacity relative to, say, 5 degrees, but they're still providing, in many cases, a significant portion of their overall heating capacity. However, sometimes there are heat pumps that don't have ratings in those extremely low temperatures that might be just as capable, and the manufacturer didn't supply data for those temperature points. So it's a little tricky, but basically there are heat pumps that are rated for those temperature points in terms of their functionality. One thing to remember is that a heat pump really isn't going to stop working when it gets extremely cold. It just may have a more difficult time keeping up delivering the same rate of heating to your home as is leaving your home, and therefore your home ends up getting a little bit cooler. So conceivably, depending on the equipment you select, there could be some extreme weather events where a heat pump might struggle. Fortunately, in New England, we don't see that, very frequently.
And I'll add anecdotally that, we had a fairly extreme weather event this past year, and the tales that we sort of heard from folks that we've consulted with who've installed heat pump systems were actually overwhelmingly positive. The people who reached out to us reached out to, praise their systems, indicate they didn't have concerns about the heating that was supplied throughout that period. We actually heard far more of that positive story than we did of negative stories. But to Terry's point, that does speak to the importance of selecting equipment that is designed for that purpose to be able to provide primary heating even down in those cold temperatures. And then the other part of the question that Kyle had sent was about cost estimates. And I'll preface by saying that without knowing the specifics of the home, the weatherization level and age of the home, it is difficult to estimate those costs. And it does also depend on the manufacturer of equipment, the configuration of equipment. But I suppose that that's a good time to plug what's on this previous slide here, which is Abode's consulting offerings. So this is actually a QR code that will take you to a link where you can schedule a no-cost consultation with Terry or another one of our heat pump specialists. And that is a great time to get into the specifics of a home, specific project goals, system designs that might make the most sense for a given home, and cost estimates depending on the circumstances of that particular home and project. So if you were to scan this with your camera phone, you'd be able to go to the website. The consultation offerings are also linked from Middleborough Gas and Electric Department's website as well. So Terry,
So I saw Tom's question
about
about the shady or sunny areas. So that's less important. In fact, really what's more of concern in terms of your heat pump location is what is a suitable location, what meets local code, and where can it get the most airflow? When you think about it in the wintertime, because there's less heat energy in that air, you need a larger volume of that air available in order to extract heat energy from it. So you really do want a good airflow. Heat pumps should be installed on stands so that they are up a foot or maybe 18 inches off the ground. We don't want them to be surrounded by snow. That's part of the reason for the stand. You could potentially clear off a heat pump that it was covered in a snow berm or something of that nature. But in general, maximal airflow is going to operate best with a heat pump. So less important as to sunny or shaded locations. And of course, those locations in terms of the sun or shade will change depending on the season anyway. So. And then there was a question, I think, about the longevity of the systems. So the longer warranties on heat pumps are generally around 12 years, although you will see lesser warranties at 10 years. And I think I've even heard of an 8-year warranty. So I think it's reasonable to consider, an average lifespan somewhere between, say, 12 and 15 years. Maybe if you're lucky, you might be able to push a heat pump longer than that. In regards to annual maintenance, there generally isn't a lot. You shouldn't really need to have the refrigerant recharged. Typically, that's about once in the lifetime of a heat pump. So unless there's some sort of a leak, which we really don't want, because refrigerant is a much worse gas for the atmosphere than CO2 is. So we don't want any leaking. But if it's installed correctly and it's not leaking, you shouldn't have to worry about getting it recharged. Some companies will offer, as part of their overall quoting, they'll offer some maintenance and servicing. You can look into that if you'd like, but generally the maintenance is fairly minimal. There is occasionally some changing of filters on the non-ducted units, et cetera. And of course, if you have ducted equipment, you're going to be changing filters like you normally would with ducted equipment in any case. But if you're reasonably capable of handling that, then that's not too difficult.
And Kyle has one here that says, I currently have heat pumps in my home on the second floor, but would like information on resources and rebates as I'm considering them now for the first floor of my home. Kevin, I think you have the rebate eligibility rules pulled up. I don't remember off the top of my head if that $2,000 cap is a per household per year, or if there's a different timeline.
Yes, per household per year.
Okay. So in that case, if it's a new calendar year, then I'd say explore away, and happy to consult with you on that. And you could be eligible for up to $2,000 in rebates for heat pumps on the first floor there.
Yep, and very easy. And any specific questions, you can just email right over to smartenergy@mged.com. And if I can't answer myself, I know two guys who can.
Right, here's another one from Kyle. Planning to replace two 30-year-old conventional AC condensers or compressors for main level central air and second level central air with Fujitsu heat pumps. Interested in rebates that may apply. Kevin had outlined the sort of eligibility requirements there. I would reiterate that the NEEP list, the NEEP cold climate heat pump list, is the eligibility requirement list. So any equipment that's listed on that NEEP heat pump list will qualify for the rebate from Middleborough Gas and Electric Department. Like Kevin mentioned, there are countless different configurations of equipment. All pretty much manufacturers are represented there. And all of the sort of efficiency factors are baked into that list. So if your contractor is proposing something in particular and is able to locate that exact combination of outdoor and indoor equipment on that NEEP cold climate heat pump list, then that system does meet the requirements for a rebate. Any more for us here, Kyle, or anyone in attendance?
Okay. Well, we're just at about an hour, which is an ideal time. But I want to thank Ryan and Terry so much. They provide such a great, invaluable resource to us at MGED. And again, any questions, please feel free to reach out to any of us in the energy services team at MGED. It was smartenergy@mged.com. And again, any questions, if I can't answer, I'll forward right on to the team at Abode, and they'll be happy to help.
Thanks all. Thanks for attending and have a great evening.
Thank you all very much.
Thanks. It was a pleasure. Have a good evening. Bye-bye.